Good afternoon, everyone. I'm Vignesh, second year EC student at EC department student at NIT Trichy. Today, I'm going to explain about my assignment with for transmission lines and wavegates ECPC 16 course. Our project is based on a multi-band impedance matching for dynamic RF systems using machine learning, which will be implemented on STM32H7 microcontroller. So I will go through the project one by one with the comparisons and the problem which we overcome and the next things which we can do on the project. First, let me start with the motivation and problem statement. The previous existing problems with the impedance matching was uh, the single band limitation. So it was just tuning for only one 2.5 gigahertz or some 5 gigahertz. But what we have done is we have created multi-band like 2.4 gigahertz, 900 hertz, and 5.8 gigahertz. Our ML model trained for with multiple inputs so that it can uh, do the adaptivity for everything. And the previous issues which were there in most of the papers like Jayang et al. Or other papers which are compared was the minimum time it took itself was 25 milliseconds, which was less in most of the cases, which was not adequate enough for rapidly changing environments like mobile IoT. So we have decided to come up with a new thing like implementing in a microcontroller with a fast ML TensorFlow Lite model, which will do it in a less than 10 seconds or at least a 20 milliseconds. The third one was high power consumption, which was also there in all of the most of the ML enhanced models. Because in ML enhanced models, the power consumption will be very high. They will be using high power systems mostly. So we have did the thing based on TensorFlow Lite, which is edge friendly power budget inference control like below 50 millivolts only it will take. So it will for longer life. So battery issue won't be a problem compared to the previous versions, and it is much better to do that. So these are the problem statement and the ideas we have took to overcome that. I will explain one by one how the ML model is trained and the data set which we have created for that through the particular presentation in further time. So yeah, so proposed system architecture, hardware and ML integration. So if an ML model or the microcontroller needs to work, it needs to get the inputs. So our first input was like input or the output. Like I will tell about both of things. So the input features of our ML model is like the reflection coefficients of all the three bands 2.4 gigahertz, 5 gigahertz, and 900 hertz, which you have said, and the temperature and the humidity. So temperature and humidity also plays a major role in the values of the impedance matching. So we have included that as well. So the matching networks is based on switched capacitor array and vector diode, which is mentioned in the slides. So based on our ML model output, these things gets changed rapidly. So the matched impedance signal is to the antenna load. The output will be changed in the antenna load, and the sensing model which we are using is basically the directional coupler and the RF detector value to measure the reflection coefficients. So these sensing model will check the values and then give it to the ML model, and then ML model will predict and then change the vector diodes and capaciting modules. So this goes like a feedback and which gets updated in a few very few milliseconds, and then this is the one of the fast proposed systems which we have known by the comparisons. So the five features are three reflection bands are three reflection coefficients are three bands, temperature and humidity, which we have generated synthetic data set, which I'll say about in the next slide. So the data generation approach. So as we can also generate the environmental simulation using CTS and other environmental tools, ADS or HFFS, but we have gone through a synthetic data set generation as environmental or other simulation makes a lot of domain head space and computational effort with a lot of data need to be generated over time. So we have used a synthetic data generation for this purpose, which also works well, but we need a lot of tuning over in the further time. So we have did that, and the machine learning model was based on the previous other comparisons using the both LSTMs and convolutional neural network, which was a hybrid thing which we have developed. So with this idea, what we are doing is we are doing a temporal learning through the LSTMs and the spatial learning through the convolutional neural network, which is generally used for the images. So this is a hybrid model which acts well. The vector diode voltages are basically in a regression, and the switch capacitor values are basically like a classification on or off like that. So the main thing which are did in this one was TensorFlow Lite version which you have used. So that is for the quantization of to the 8-bit quantizing of the model. They have also quantized to 8-bit precision to reduce the size of the model and to deploy on embedded device. TensorFlow Lite basically makes it to be easier to run on a embedded device. Basically STM32 which is the preferred one for the 480 megahertz which it possesses. So yeah, that is the thing. And yeah, target goals was less than 10 millisecond and the power of less than 50 millivolts, and the reflection coefficient, like reflection, was less than 0.1. These are the equations which I have used to create everything, the ML equations and the transmission lines equation which I have used. So the comparisons to the previous papers was done, like they have used the machine learning model, deep neural network model, and the CSM model separately in different things, but we have made a hybrid one of CNN and LSTM, with the latency being the very lowest of all. Like we are yet to check with the hardware things, or we can check in the further time. This is a proposed architecture, and the power consumption being less with many changes and the further things, it can be even made to even less value. Yeah, that is it. And we have designed an AI based system as of now. We can easily implement it on a STM or a ESP device, whatever it is possible. This doesn't require server overload, server cloud, which was because everything can be done basically on the ESP controller. We can also improve adopt federated learning, which is basically doing it on every nodes and then collecting the data and then adding the weights or changing the weights of the ESP or the STM microcontrollers in the ML side, so that things gets even more smoother without much overhead in the device. So that can also be done with the improved data testing and quantized performance. Yeah, these things all can be done in the parasitic effects on real PCBs. This is the future role ahead for the problem statement which I have taken. So that, thank you for the opportunity being provided. Now let me explain about the code which we have did in the GitHub page. The code is in this one. Yeah. So this is the collab notebook code which you have generated. So it is also put on GitHub for with the README file on it, with a few citations being added to it and other things mentioned. You can also check in the GitHub page and also in the collab notebook. Collab notebook will be even easy, but right now I am checking on the GitHub page to make it uniform for everyone. So everything was mentioned here as well in a simple way. So yeah, the comparisons. These are the proposed approach, but not yet to be achieved. So the TensorFlow light model is implied, and the synthetic data generation is adding Gaussian noise and other sinusoidal approximation to maintain environmental characteristics. The training set and the LSTM, the ML model which we have created using LSTM and dropout layers to reduce the size of the model dropout for faster computation and all. So and then we are using Keras because that is what makes it quantization and embedded like deployment in the TensorFlow Lite model. So we are using TensorFlow libraries for that reason. So after generating everything, we are just checking the layers and all in a printing format, and then we are training the model in the Collab notebook. So we are getting the outputs for everything in that, and it is just doing it in a less epoch because the conversion early stopping is there which you have created. So if the validation loss doesn't go improves for a larger time, it will eventually stop. So we are using that as well, so that it stops eventually. With the larger data training, that can also be avoided because it converges only after a larger time. So as we are using lesser data, so we should try adding early stopping so that it converges way before it doesn't go 50 epoch and waste much of the computational power. So these are other parameters for the outputs. Validation loss is also checked again. So voltage is also checked again with the classification report being done. We have achieved 25 to 30, 40% as of now with the synthetic data set, but with the environmental data set, we can even achieve a lot of things. So yeah, this is the quantization thing for TensorFlow Lite model. So this is the complete code for our project, which can also be improved in a lot of ways. This possesses many future applications and many future improvements and advancements to be done for the project. With the time, with the time and advancements, these things can be improved a lot. These are the proposed ideas so much. So thank you for the time. Thank you for your time. Shining off, Ignatius.